The synthesis of amines is going to be the topic in this lesson, and we're going to go through several syntheses for amines. The first few are all going to be review, things we learned earlier in the course, so I'm going to present them very briefly. But then we're going to learn several new syntheses as well, including the Hofmann rearrangement, including the Curtius rearrangement, the Schmidt reaction, the Gabriel synthesis, and reductive amination. Now, this lesson is part of my organic chemistry playlist. I'm releasing these lessons weekly throughout the school year, so if you want to be notified every time I post a new lesson or when I begin working on a new playlist, subscribe to the channel, click the bell notification. All right, so we're going to start these syntheses with a review of several reduction reactions. And I say review, one of them actually is new, but the rest are all review, and the one that's new is very similar to the ones that are old. So in this case, we'll start with just reduction of a nitro compound. And you guys learned back in the side chain reactions of benzene section that we can reduce a nitro group either with catalytic hydrogenation or with one of three active metals, either zinc, tin, or iron with acid. And in this case, you can turn your nitro group to an amine group instead. So there's the first one. We've just made aniline. Next one here is the reduction of a nitrile, and we can turn our carbon-nitrogen triple bond into a carbon-nitrogen single bond with lithium aluminum hydride here. And so we've added 2 H's to the carbon and 2 H's to the nitrogen overall. Cool, finally we've got reduction of azides, and this one I don't actually think we covered earlier in the course, so it's new here, but it's overall very similar to what we saw with this guy here. And in this case, we're going to lose 2 of those nitrogens in the process. But the remaining nitrogen of the original azide ion is going to be part of now an amine, once again with lithium aluminum hydride or catalytic hydrogenation. So the last reduction we're going to take a look at that synthesizing amine is the reduction of an amide. And you guys might recall with lithium aluminum hydride and H3O+, you're just going to lose the oxygen here as your leaving group instead of that nitrogen. So leaving you with this one in case. And I want to put this present it separately from the other reductions because it is going to look very similar to a new one here, the Hofmann rearrangement, and students often confuse the two, but the final product is going to actually end up being 1 carbon different. So in the case of lithium aluminum hydride reduction, we're going to lose this oxygen. So in the reduction reaction, replace it with 2 hydrogen atoms. Now that carbon's bonded to 2 hydrogens. But in the case of the Hofmann rearrangement, we're going to find out we're going to lose the entire carbonyl as a part of the process. So we not only lose the oxygen, we lose a carbon atom in the process here as well. And so we're going to end up with an amine in either one of these reactions. And starting with the same reactant, though, we see we've got the same number of carbons in our product as the reactant with lithium aluminum hydride, but 1 fewer carbons in our product than our reactant in the Hofmann rearrangement. So let's take a look at the mechanism for that Hofmann rearrangement. So before we dive into this mechanism, I just want to point one thing out here. So some of you won't even see this reaction in your curriculum. And for those of you that see it, some of you won't be on the hook for the mechanism. And for those of you that are on the hook for the mechanism, some of you will only be on the hook for the reaction to form the isocyanate intermediate and probably not the hydrolysis of it. So, and then some of you, very few of you, will probably be on the hook for the whole thing. So, but we're going to cover the whole thing, but I will point out when we get to that isocyanate intermediate. For those of you, that's all you're on the hook for. So, all right, let's take a look at this here. So first thing we're going to do here is nucleophilic attack, and we're going to do nucleophilic attack on the bromine here, break the bond to the other bromine. So now your nitron is going to be bonded to a bromine and still 2 hydrogens, and that's when your hydroxide here is going to come and deprotonate. Now, one thing to note is we did nucleophilic attack first and then deprotonated a hydrogen second. There are reports of the mechanism out there in the literature where the hydroxide comes and deprotonates first, and then we'll do nucleophilic attack second. So, but you're more commonly going to see it represented this way, which is why it's the way I'm going with. All right, so from here, we're going to get our big rearrangement. And in this case, what you're going to have happen is you're going to have this bond right here is going to break, and this carbon's going to come and bond to the nitrogen. And the nitrogen's going to have the bromine leave to make room for that to happen as a leaving group. So that's what's going to have happen here. So in this case, if we take a look at what this looks like, Now we're bonded to the nitrogen instead. That nitrogen is still bonded to a hydrogen, but now it's bonded, the nitrogen's bonded to this carbon still. That's bonded to an oxygen. Now, one thing to note here, this carbon right here is going to have a positive charge, and our nitrogen still has a lone pair, and so it's a resonance stabilized carbocation here, and so we could dump this in to form a resonance structure where the nitrogen would have the positive formal charge, and it turns out that's going to be the major resonance contributor. And so what you'll often see as well is you'll see these electrons dumped into here from the get-go. That way you're already into a position here where you've got that nitrogen carbon double bond and the positive formal charge on the nitrogen, and oftentimes you'll see only the major resonance contributor here presented. Sometimes you'll see both, sometimes you'll see just the second one. You usually don't see just the first one. So, but here we've got this lovely resonance stabilized intermediate, and then we'll have another hydroxide come in and deprotonate. Cool. This is the species we refer to as the isocyanate. Get that in there. So cool. Some of you on the hook for the mechanism only up until this point, forming that isocyanate intermediate. So, but this is going to undergo hydrolysis. It'll lose CO2 in the process and eventually form our product amine here. Let's take a look at how that works here. So we're going to need a water molecule here. In fact, I'm going to erase this water molecule and just draw another one in. So this water molecule is going to come and attack the carbonyl, push the electrons over to the nitrogen. Technically, it could push it over to the oxygen as well, and you got some resonance going on. So you've got a positive formal charge on the oxygen, negative formal charge on the nitrogen. And what you're going to have happen, and often the way we represent this here, is we do a little proton transfer and we say plus H plus minus H plus. And so you're going to protonate this nitrogen and you're going to deprotonate the oxygen. And it's not that this nitrogen deprotonates the hydrogen. There might be too far apart for that to happen. But both these proton transfers are going to take place. So the nitrogen gets protonated, the oxygen gets deprotonated. You end up with this lovely species, which is a type of carbamic acid, I believe. And then from here, we're going to do the same exact thing, and we're going to represent it in a very similar way. We're going to say plus H plus minus H plus, and we are going to plus H plus. We're going to protonate the nitrogen. We're also going to deprotonate this oxygen right here. Giving you this lovely intermediate, and here's where we're going to form the carbon dioxide. So wherever these electrons come down, so give you a carbon double bonded to two oxygens, but so we don't violate the octet rule, this bond has to break. So, and that's where we get our final product here. So you're going to get this guy left over on this half of the molecule, and then obviously plus carbon dioxide for the right-hand side. And that is the rest of that hydrolysis mechanism. So again, some of you are going to be on the hook all the way only up until isocyanate formation. So, and a few of you will be on the hook for the whole thing, including the last half, the hydrolysis of that isocyanate to form your amine and CO2. Now this is important. We'll find out that the next couple of syntheses also end up going through an isocyanate intermediate that also gets hydrolyzed in exactly the same fashion. And so when we cover those two syntheses, I'm not going to cover the mechanism all the way through to like we did here. I'll probably just kind of more summarize and just say, hey, then we go from the isocyanate all the way to the amine and CO2. So the next reaction we're going to cover is the Curtius rearrangement. It's going to have a lot of similarities to the Hofmann rearrangement here, and we're still going to ultimately lose a carbon. But in this case, instead of starting with an amide, we're starting with a carboxylic acid, but we will lose a carbon in the process along the way to forming an amine. Cool. Now, part of this we already know, and we'll take a look at kind of we're not going to look at the mechanism with all the arrow pushing detail, but we'll take a look at what we do know about this mechanism. And in this case, if you look at your carboxylic acid, SOCl2, you guys already know that converts a carboxylic acid into an acid chloride. So and that chloride's a good leaving group. Then we're going to do nucleophilic acyl substitution with the azide ion replacing the chloride. And then this azide ion, let's just show you what that azide ion looks like a little bit. So in this case, what you're going to have happen is a similar rearrangement to the one we saw with the Hofmann rearrangement, and this carbon's going to end up coming and bonding to this nitrogen over here. To make room for that happening, we're going to break that bond, and this is where nitrogen gas forms and bubbles away. And then we'll also come back here and have this guy form a double bond to the carbon that's double bonded to the oxygen, which is where you form your isocyanate. And so in this case, so this carbon now is bonded to the nitrogen. That nitrogen is double bonded to a carbon. That is double bonded to an oxygen still. And so there you've got your isocyanate. So, and then again, it undergoes hydrolysis to turn into your amine plus carbon dioxide. So notice didn't go through any detailed arrow pushing here, but wanted to give you just kind of a mechanistic outlook of how this reaction is actually happening. So lots of similarities to our Hofmann rearrangement, and we'll see the same in our next one, the Schmidt reaction. All right, so your Schmidt reaction accomplishes the exact same net result as your Curtius rearrangement here. And you've got your carboxylic acid, same one here, and it's going to form exactly the same amine here as well. So it's just an alternative to actually carry out the exact same process. And the way this works, instead of going through an acid chloride, we're just going to add sodium azide with sulfuric acid to bypass this process and go straight to this intermediate right here, this acyl azide, we say. And from there, it's pretty much the same. That acyl azide is going to turn into isocyanate, and that isocyanate is then going to get converted into your corresponding amine with one fewer carbons, and then carbon dioxide. All right, the next amine synthesis is the Gabriel synthesis. It starts with phthalimide here, and before we get anywhere caught up into the Gabriel synthesis itself, we got to talk about why it's necessary and what it accomplishes. So the Gabriel synthesis is another template synthesis. It is for making primary amines, and it turns out primary amines are rather difficult to make apart from this Gabriel synthesis by normal conventional means you might have learned already. And I'm talking about SN2 reactions. You might think, oh, Chad, you know, we can do this. So if we take ammonia and add an alkyl halide, we can do backside attack, kick off that leaving group. Get this lovely intermediate. It's going to get deprotonated. Maybe we just write minus H plus. Not too concerned about the arrow pushing mechanism here. And voila, we get our lovely primary amine. Done by reactions we already know. And problem is we're not going to get a good yield, and we're technically not done. So it turns out that this lovely species right here is on par about the same nucleophilic strength as the original ammonia that you started with here. And so all of a sudden now, you know, let's say you've got, 50 of these guys reacting with 50 of these guys. Well, by the time the first 10 of these react to form 10 of these, now you've got 10 of these, you still got 40 ammonias, you still got 40 of the alkyl halide, and these guys are like, oh, let us react with the alkyl halide. And so some of that's going to happen as well. And so a couple steps down the road, you're going to have now a secondary amine, and some of these get to react with the alkyl halide potentially. And you get a tertiary amine, and then some of these get to react with the alkyl halide, forming a quaternary ammonium ion. And all of a sudden, now you've just got a huge mixture in your solution that includes primary amines, secondary amines, tertiary amines, quaternary ammonium ions. And so if your goal had been to just make this one primary amine, you didn't do a great job of it. And so we've got to come up with an alternative to this, or else you're just going to have a big mixture of different SN2 products. And so that's what the Gabriel synthesis is for. It's for making a primary amine in a much better yield than we can accomplish with SN2. So this is a funky word here. only time I can think of where you see a pH and a TH side by side like this, and this is phthalimide, the pH, the F sound there, so phthalimide, and it is not an amide, it's an imide. This nitrogen's not just adjacent to one carbonyl, it's adjacent to two carbonyls. And so turns out this nitrogen can have delocalization with two carbonyls, and whereas an amide is not the most acidic thing in the world, an imide with an I is a little more acidic to the point where it can be deprotonated by potassium hydroxide here. So got potassium hydroxide, and we're going to have that hydroxide ion come and deprotonate this hydrogen, first step. And then we're going to react it with an alkyl halide. This thing's a great nucleophile, and so now you're going to choose your alkyl halide of choice. And in this case, if this was the amine I was looking for, then this would be the alkyl halide I'd be using. And so in this case, I'm going to go back in and throw in our 3-carbon alkyl halide, and this guy's going to come around and do backside attack. What's nice, though, is that whereas an amine here itself can act as a nucleophile, an imide cannot. So the imide, again, that lone pair is delocalized with resonance with both oxygens here, and as a result, it's much more stable than an amine, and it's not a good nucleophile. With a negative charge, it's a decent nucleophile, but neutral, not so much, and so we don't have to worry about this reacting any further. And so from here, an imide you can look at as another carboxylic acid derivative. And so we have a couple of different options here. So from this stage, we could add barium hydroxide. And the key part here is the hydroxide, a strong base. And just like all those carboxylic acid derivatives, what you're going to do is nucleophilic acyl substitution. We're going to break both of these bonds with the nitrogen acting as a leaving group, so to speak. So we're going to do it twice. Once with the carboxyl group on top, once with the carboxyl group on bottom. We're going to have hydroxide come and attack. So, and eventually end up with something looking like where the OHs of the hydroxides have replaced the amine group here. So, but if you recall, just like we did with carboxylic acid derivatives, when this happens under basic conditions and barium hydroxide is a strong base, then these end up deprotonated as just carboxylates there. Now, they're not my desirable product. This is just what I'm going to recycle, and I'll probably turn this back into phthalimide later so I can do more Gabriel synthesis. What I want, though, was the leaving group, and that's actually the product of interest here. And that leaving group, that nitrogen along the way, is going to get protonated a couple times, forming your primary amine in a nice creative way. Now, I do want to make you aware of one other way this reaction is actually completed. Instead of barium hydroxide, you will see it also completed with N2H4 hydrazine, or NH2NH2. So, and in that case, you end up with a slightly different reaction. Instead of hydroxide doing your nucleophilic acyl substitution, it's going to be the hydrazine doing it. So, in your hydrazine here, one of the nitrogens hydrolyzes one side, one of the nitrogens hydrolyzes the other side, and there is the remnants of your hydrazine right there in your product. And then the other two hydrogens that are missing are the ones that actually result with your primary, the two hydrogens on your primary amine. And so depending on which of your reagents you do step 3 in with here, either barium hydroxide or hydrazine, it doesn't change your amine product, which is the goal in this reaction, but it will change your side product here. But in either case, either one of these, it's probably going to be recycled and converted back into phthalimide so that you can do Gabriel synthesis another day. All right, so the last synthesis for amines we're going to look at is not only a synthesis of amines, it's a reaction of amines. And so it turns out one of the reactants is either going to be ammonia or primary or secondary amine, so it's a reaction of these amines, but it's also going to form amines as well. And it turns out it's going to form an amine that is 1 degree more substituted than the one you use. So like ammonia is not really an amine, it's an completely unsubstituted, but when you do reductive amination, it's going to form a primary amine, as we'll see. When you start with a primary amine in reductive amination, you get a secondary amine, as we'll see. And when you start with a secondary amine, you'll get a tertiary amine end result, as we'll see. So it always gets 1 degree more substituted than the original amine you start with. Now, notice this is reductive amination, not animation. It's going to be difficult to say, and I guarantee you're going to say it wrong at least once, but it's not animation, it's amination. So, and we'll see why they call it reductive amination in just a second here. So you guys learned when you take a ketone or aldehyde and react it with either ammonia or a primary amine, you form an imine, where your carbon-oxygen double bond is converted into a carbon-nitrogen double bond. And if you start with ammonia, your nitrogen is still bonded to a hydrogen, but if you start with a primary amine, your nitrogen is still bonded to whatever alkyl group you had as part of your primary amine. Now with a secondary amine, it's going to be a little bit different. You guys learned that instead of ending up with a carbon-nitrogen double bond, you end up with an enamine, a carbon-carbon double bond instead. So once again, we've got, with ammonia, the intermediate's an imine, also with the primary amine, but with the secondary amine, your intermediate is an enamine. Cool. And now all these need to be reduced. So it's amination and it is reductive as well in the second step. And the most common reducing agent's a little bit funky. This is sodium cyanoborohydride. So kind of like sodium borohydride, where one of the 4 H's in sodium borohydride, NaBH4, is replaced by this cyano group. So and it turns out this decreases its reactivity just a little bit. So this is less reactive than sodium borohydride. Now, it turns out you can also do this with catalytic hydrogenation, H2PDC in this step. You can also actually use sodium borohydride. The problem, though, is that you mix all this together in one step, and if you use sodium borohydride, some of it's actually going to reduce your ketone to a secondary alcohol, or your aldehyde to a primary alcohol. And so, but if we use sodium cyanoborohydride, it'll reduce your imines or enamines, but it actually is not strong enough to react with your ketone or aldehyde. So it's kind of a nice choice, and it's the most common one, so it's the one I'm going to kind of run with here. So, but in this case, you're going to reduce that carbon-nitrogen double bond to a carbon-nitrogen single bond. And so we've added a hydrogen to the carbon and a hydrogen to the nitrogen. Same thing when we started with the primary amine. And with the enamine, you'll just reduce the carbon-carbon double bond. So if we go back and take a look here, again, we started with a primary amine here and a secondary amine here and ammonia here. And now we've ended up with a primary amine here, a secondary amine here, and a tertiary amine here. And so again, ammonia, which is unsubstituted, goes to primary. A primary amine results in a secondary amine, and a secondary amine results in a tertiary amine. And so again, this is your reductive amination. Not only is it a reaction of amines, but your product is also an amine, so it's also a synthesis of amines. So this is a good bridge because in the next lesson, we're going to start covering all the reactions of amines, and technically we've kind of, in a certain way, covered one already. Now, if you found this lesson helpful, would you consider giving me a like and a share? Best things you can do to make sure other students get to see this lesson as well. If you're looking for the study guide that goes with this lesson, if you are looking for practice problems on amine synthesis and reactions, check out my premium course at chadsprep.com.